To name binary ionic compounds, I use the following rules. First, the name of the cation comes before the name of the anion. Second, cations take the name of the element. Third, anions take the root name of the element and add IDE to the end. And a polyatomic anion, which is an anion but made up of more than one element. A monoatomic anion is just made up of one element. A polyatomic anion uses its own name. And same with the cations, they use their own name as well. I forgot to mention that. But these are best illustrated with examples. Take table salt, NaCl. Now what's helpful when learning to name ionic compounds to break apart the cations and anions to their charges. Na plus, Cl minus. That way it's easier to name, and it's just helpful to become accustomed to the differences in charges, because they're going to become very important later on. But for now, it's easier to distinguish the anion and cation. Sodium here is the anion, or the cation, and it's going to take the name of the element, which is sodium. The cation here is chlorine. Chlorine takes the root name of the element and adds IDE. The root name is chlor, and then IDE, chloride, sodium chloride. Sometimes finding the correct root word takes a little bit of getting used to, but most of them are pretty intuitive, in my opinion. And for naming these compounds, it's not important how many of the cation to anion ratio there is. If there is more cation or anion, it's not apparent in the name. The charges are what explain what the compound name, or what the compound will look like. Because I know that sodium has a +1, and I know that chlorine has a -1, so it's unnecessary to distinguish one sodium, one chlorine. So for the following example, let's look at lithium and nitrogen. If I want to name this compound, I look at the cations and anions. And the cation is lithium. It has a +1 charge. And the anion is nitrogen, and it has a -3 charge. So I go over here, and it's 3 away from these noble gases, so I know it's a -3. Everything in this row is -3, this is -2, this is -1. These over here are +1 and +2. And all of these transition metals will have different charges. But if I want to name this, I look, see that the cation is lithium. I was about to write cation. Lithium, and the anion is nitrogen, so I take the root word and add "ide." Lithium nitride. Now, it's good to notice that in the name there is no indication of how many lithiums there are and how many nitrogens. And that is because the charge of lithium and the charge of nitrogen are known. They are -3 and +1. So when I look at this, I already know that there is going to be 3 lithiums to 1 nitrogen because of the charge difference, because these are going to be neutrally charged. Now I need to talk about situations where a transition metal is usually involved. And transition metals are usually these elements. And they can have multiple charges. Not at once, but take for instance iron. Iron can have a +2, or iron can have a +3 charge. And if I had iron and oxygen, which has a -2, how would I distinguish between the two? Because if iron 2 with a +2 charge and oxygen were ionically bonded, this would be FeO, because this is a +2 and this is a -2. But if these two were ionically bonded, this would be Fe2O3. It would have to be up to, I would have to get both charges up to a 6, so they would even out. Multiply this by 2 is +6, multiply this by 3, and this is -6. And these two compounds are different. FeO and Fe2O are not the same thing. So in order to distinguish transition metals or any other type of cation that has different charges, we attach a Roman numeral to it. So this would be iron 2 oxide. And this would be iron 3 oxide. And that way people can tell if it's a +3 iron or a +2 iron. Otherwise, no one would be able to know. So let me take another example of a transition metal. Lead can exist as +2 or +4. And say I wanted to combine it with chlorine. What would the names of these be? Well, this is a +2 and this is a -1. So I'm going to need 2 chlorines for every 1 +2 lead. So the chemical formula would be this. And the name would be lead. It has a charge of 2, so I put a Roman numeral of 2. And then chloride. Still using the same system as before. The only difference is that these have Roman numerals in order to distinguish the charge. And this would be lead Cl4, because I would need 4 chlorines in order to satiate this +4 lead. It's lead 4 chloride. That really covers the transition metals. All of these really need to be simply looked up. Aluminum can have a +3, mercury can be a +1 or +2, copper can have different values. All of these really just need to be looked up and find out what charge each one of these transition metals will have. It was not necessary before, because for nitrogen, oxygen, fluorine, chlorine, lithium, beryllium, magnesium, sodium, all of these are known. They exist almost always as these charges. And now I need to talk about polyatomic ions. And polyatomic ions are or cations. Anions or cations. Polyatomic ions are ions that are made up of more than one element. For example, OH minus is called hydroxide. And this is an anion made up of an oxygen and a hydrogen. And there are countless of these anions and cations. Let me list a few. I'm not going to list all of them. I'd be here forever. Here's another one. NO3 minus, and this is nitrate. Or another really common one is phosphate. It has a -3 charge. And I'll put one cation as well, I guess. This one, NH4, yeah. This is ammonium. Now the names work exactly the same way as they did before, except for when naming the anion, I don't put IDE at the end, I just use the name. So I just use the name for both. So for example, if I wanted to do NaOH, the cation, oh, I forgot the Na, I forgot the A. Cation is Na plus, which is sodium. So I take the cation, use the element's name, sodium. And then normally for the anion, I would have taken the element and added IDE at the end. But here I can see that the cation is OH minus. And it's a polyatomic ion, as more than one element, in which case I just use its name, sodium hydroxide. In this case, I guess hydroxide already had an IDE at the end, but that's just a coincidence. Let me take another example. Suppose I'll use phosphate. I have K3PO4. Here the cation is potassium. Which is a +1, like everything else in this first row. And phosphate, which is a -3. So in order to name this, I disregard how many potassiums there are. It does not matter for the names of ionic compounds. For the name of covalently bonded things, it will, but for now it doesn't matter. So this would be potassium, and then I take the name of the anion, phosphate. And in this case, there is no IDE at the end. The last example, it just happened to have an IDE, but it's not required. The correct name of this is potassium phosphate. And I'll do one more example where I use a polyatomic cation and a polyatomic anion. Let me say I have NH4 and NO3. here the cation is ammonium, and the anion is NO3 minus. To name this, I use the name of the cation and then the name of the anion. And that's it. It's really a simple process. The only thing that is a little bit challenging is the polyatomic ions, and it's mainly because of the names, and most of them are not familiar. Most of these polyatomic anions are different functional groups from different fields of chemistry, like organic chemistry or biochemistry. And they've named these different functional groups and have phosphates, all these other different groups that are named that are common in different sciences. But in the beginning of general chemistry, they're all very unfamiliar, and that's what makes them a little bit more difficult to deal with. But it really is just a matter of looking up the name, looking up the charge, and naming them, because the quantity of cation and anion is unimportant to the name.